Okay, any questions from last time about lecture 5? We covered a large number of evolutionary algorithms that increased in complexity, and in and in assignments 8, 9, and 10, you're going to be implementing a few of those evolutionary algorithms to evolve your robot. Any questions? Okay, if not, let's carry on. You're working, undergraduates, you're working on assignment 3. Graduate students, you're working on assignments 5 and 6. And today we're going to talk about physical simulation. So in lecture 4, we dove into a little bit of neuroscience and talked about neurons and synapses and how you'll be simulating a neural controller for your robot that transforms perception into action. Then we switched from neuroscience to evolutionary biology, and we boiled down Darwinian selection to an algorithm, which you will be encoding as well. And today we're going to do a little bit of physics and talk about physical simulation, how you actually construct the virtual world for your robot and the virtual robot itself. And of course, at this point in the class, you have a little bit of experience with physical simulation already. Okay, I'm going to leave things in this mode, if that's all right, so that I can still see chat. Please stop me and ask questions in chat if you have any, and we'll proceed as follows. Okay, so let's start by comparing physical simulation to what came before it, which was 3D computer graphics. So if you wanted to make a virtual world before the advent of physical simulation, you had to simulate all of the physics yourself. How was that done? You defined all of the objects that made up your virtual environment, and you had to define the position, orientation in 3D space, and the shape of every object at every point in time in your animation. Once you had described all of these in sufficient detail to the computer, you would usually then turn things over to the computer, and it would grind away and render one frame after the other, and at the end stitch together. It would render that frame, and then at the next frame, you would have to tell the computer how each object had changed from one frame to the other. So for example, if you wanted to simulate a ball that was placed above the ground and fell towards the ground, you would need to use 9.8 meters per second squared to work out how the vertical position of the object changed between time step t and t+1. So for every frame, you were defining some either directly or indirectly, depending on the 3D graphics engine you were using, the changes, the deltas in position, orientation, and shape of each object at the next time step. Obviously, if you were dealing with soft objects, you also had to take into account deformation. If this ball is soft and fell towards the ground and came into contact with the ground, how did the shape of the object change when it came into contact with the ground? Once you defined all these deltas, now the computer had the new position, orientation, and shape. At time t+1, it would render the scene, and around and around you go. And as you can tell from this cartoon example that I'm describing, this was a very labor-intensive process. Modern 3D computer graphics engines obviously automate some of this for you. Most of them, of course, have a physical simulator underneath. So how does physical simulation differ from this manual process? Well, it's not completely automatic. As you already know by now, you are still required to provide the computer with a fair bit of information about your virtual world. Again, for every object, like in computer graphics, you need to describe the position, orientation, and shape of the object, but you also need to define some additional physical parameters, like, for example, mass and friction, because the computer is going to use those physical properties to determine how these objects change, rather than requiring you to tell the computer how these objects change from one time step to the next. Much of what the physics engines do for you, and PyroSim, which is a wrapper you're using in this class, a robot simulator for Python, is to hide some of these physical details from you. Regardless, the physics engine needs to know position, orientation, shape, at least position, orientation, shape, mass, and friction for every object in the virtual scene. You also need to tell the physics engine how the relative motion of objects are constrained. In other words, how they're attached to one another, which is joints, and we've talked about that a little bit. Once you've set the initial conditions for all of the objects in the scene, you can then start the simulation, and now at time step t+1, t+2, t+3, you can sit back and watch the physics unfold. You no longer need to be involved in the process. How does a physics engine know how to update the position and orientation and shape of objects from one time step to another? It depends on the physics engine, and it gets really complicated really quickly. But all of them share some very basic pieces in common, and we're going to talk about some of those basic pieces today. The most basic piece of any physics engine is hopefully an equation you recognize from high school physics, which is F equals ma, or force equals mass times acceleration. In the case of a physical simulator, it rearranges these three terms into acceleration equals force divided by mass. So at every time step in a physics engine, the main thing that a physics engine is doing is visiting every object in the virtual environment and computing all of the forces that are acting on that object and summing all of those forces together. The physics engine now knows the sum of forces acting on each object and can plug those sum of forces into this equation, divide that sum of forces by the mass of the object, and the physics engine gets back the acceleration of every object in the physics engine, in the virtual scene. The physics engine knows the current position of every object, so it can then update the position of every object based on that object's acceleration, which gives the physics engine the new position and the new orientation of every object in the physics engine. You might again remember from high school physics that there are two different kinds of acceleration. There is linear acceleration, how much something is the rate of change of something along the horizontal axis, inward and outward on the screen, and upward and downward for our purposes. And there is also angular acceleration, the rate at which something is changing around the x-axis, y-axis, and z-axis. So again, it's not shown on this slide here, but there are a bunch of different kinds of accelerations that are acting on each object, and those accelerations allow the physics engine to compute the new position and the new orientation of every object at every time step. What are some of the forces that you think are acting on objects in a virtual environment? If you want, you can go ahead and type it right into chat. Some of the forces that are acting on objects are a little more obvious than others. You've started to create virtual robots and virtual environments already. What are some of the forces that are acting on those objects? Obviously, gravity, as we can see here. Yeah, Piper mentions a normal force, absolutely. You'll notice in the little cartoon example here, we have a ball that's been placed above the ground, and one force is gravity, which obviously accelerates the object downwards towards the ground. As Eli mentions here, normal force from the ground. So once the object comes into contact with the ground, if we're simulating physics, that object should not pass through the ground, but should suddenly decelerate and come to an acceleration of 0. It should stop moving altogether. The way that most physics engines do this is when two objects come into contact with one another, they push against one another. In this case, in this cartoon example here, the floor exerts a force on the object, pushing it upwards, and the strength of that force is computed to be exactly opposite to the force of gravity pulling it down. So the force, when the object comes into contact with the ground, at that time step, gravity is pushing down with 9.8 meters per second squared, is pushing down with a certain force, and the ground is pushing upwards with the exact same force, and those two forces cancel out. Remember that I mentioned the physics engine is summing all of the forces that act on an object. If you have, you might have noticed with some of the objects, we're working with cubes here. When they start to grind along the ground or roll along the ground, they eventually come to a stop. Why do they come to a stop? Why do they decelerate? What force is causing that particular change in acceleration? When you made your towers and they fell over, why did those objects not continue sliding along the ground indefinitely? As Jared mentions, friction. So friction is another important force here. Lots of different forces you can add into your physics engine that influence the behavior of the objects in your virtual environment. Okay, so throughout this lecture, you're going to see a couple of code snippets. These are code snippets taken from a different physics engine called ODE, which stands for Open Dynamics Engine. I put a link to some of the ODE documentation. These links are all optional. This is just for those of you that are interested in physical simulators and how they work. As I mentioned, there's lots of different ones. In this class, we're using PyBullet. We used to use ODE in this class. So I think it's instructive to actually see some examples of physics engines under the hood from not just the physics engine you're using, PyBullet, but a different one, which is ODE. In previous years, for students that worked with ODE, they had to implement a lot of the details of the physics engine itself. So ODE had you do a lot of the heavy lifting. PyBullet is a more modern physics engine, and it's automated, and it hides a lot of the dirty details of physical simulation from you, which is good for your purposes. It allows you to focus on robots and evolving robots. But today we're going under the hood to see how how physics engines actually work. What you're looking at here is some of the code that would be run at the beginning of a physical simulation. So this is before you start actually simulating the scene. You're setting the initial conditions of this world. In ODE, you create a world itself. You set the gravity of that world. So you can simulate Earth, you can simulate Mars, you can simulate the moon. Some other things we're going to talk about in a moment, we'll get to in a moment, are contacts and contact spaces. Contacts and contact spaces is how you tell the physics engine what to do when pairs of objects come into contact with one another. So for example, here's a pair of objects, a ball and the floor. We want to tell the physics engine that these two particular objects should not penetrate one another. This is not okay. This is okay. Certain other pairs of objects, you're going to tell your physics engine that it is okay for them to interpenetrate. What are those pairs of objects? If you tell a physics engine that a pair of objects should not interpenetrate, then if they do happen to push within one another by a small amount, the physics engine will apply forces to pull them apart again. You can tell the physics engine to not do that. You can tell it that pairs of objects are allowed to overlap with one another in the virtual scene. Again, in PyBullet, this is sort of done automatically for you. What are some pairs of objects that are allowed to interpenetrate in your environment? Connected links. Yeah, Tyler's right. Exactly. So obviously, if I'm defining my lower arm and my upper arm and connecting them by a link, they may overlap by a little bit depending on how I rotate my arm. I don't want the physics engine trying to separate my connected body parts. Okay, we'll talk about contact spaces and contact groups in a moment. Some other things you can do is talk about, you can define the friction in the world. So the floor that makes up your world, is that sandpaper? Is it very rough? Does it have high friction? Or is it ice? Does it have very low friction? Can things slide along it? ODE allows you to set global properties sort of in general, but you can also specify the material properties of individual objects. Okay. In ODE, the parts or the physical objects in the world were called bodies. In PyBullet, they're called links. Doesn't really matter for our purposes. Here you can see the nuts and bolts of how this is actually defined in ODE. In ODE, you would set a box. You would define the 3D geometry of the thing you're creating, a box or a sphere or a cylinder. You would then define the distribution of mass within that object. In this example here, you're defining an object that is a 1 by 1 by 1 kilogram box. You could increase and decrease the density inside that box. And then you could also adjust it with another term. This is part of the reason why we eventually moved away from ODE. So a little bit overly complicated. Basically, in lines 7 and 8 here, you're setting the mass of the object down here, and we are then setting the position of the body. So at time step 0, we want the object to be set at x equals 0, y equals 6 units off the ground, and z equals 0, and that's the initial position of the object. Yeah. Okay, again, in PyBullet, you're doing this a little bit differently, but we're setting the initial properties of an object. So that's the mass and position of an object. Another aspect of a 3D body, hopefully you can all see my cell phone here. You can all see my cell phone. Okay, is to set the 3D orientation of an object. At the moment in your code, you cannot set the orientation. The object, when you define it, is always upright. For our purposes, this probably doesn't matter too much, but as you move on and you start to make a robot of your own design, you might want to create a diagonal leg, or you might want to place some 3D objects at different orientations in three-dimensional space. For those of you that want to play around with that now, you can jump ahead to learning module P, tips and tricks in Ludobots. And if you reference steps 26 to 28, you can see how to actually unlock this functionality in your code. At the moment, it's locked and hidden, but if you want to play around with it, that's perfectly fine. Okay, how do you do that? Typically, if you want to define the orientation of an object in three-dimensional space, you need 4 numbers, and there's different ways you can do this. One way to do this is to use what's known as a quaternion. Quaternion requires 4 numbers. The first 3 numbers define an axis in three-dimensional space, and you're going to assume that the orientation of your object lies along that axis. And then the 4th number, theta, represents how that object is rotated about that three-dimensional axis. As you can probably imagine, quaternions are a little bit difficult to work with. It's a little bit difficult to imagine in your mind the 3D orientation you want for your object, and then to work backwards to the x, y, z, and theta required to define that orientation. So again, for most purposes, we don't need to work with quaternions. You can get away with something a little bit simpler. In ODE, the way you would do this is to work not with a rectangular solid, but to work with a cylinder, because a cylinder, once you have it along a long axis, it obviously doesn't matter what the rotation of that object is about that long axis. It's always going to look exactly the same. So we can get rid of the theta and reduce our definition of how something is oriented in three-dimensional space to just 3 numbers if we're willing to restrict ourselves to working with cylinders or something that is rotationally symmetric about the axis along that we want to place our object along. So in ODE, there was a function called set rotation, where that rotation was to rotate the object or place it along this axis here. Okay. If an object is a sphere, we don't need to bother specifying its orientation at all, because no matter what that orientation is, it always looks the same. Okay. Again, specifying the 3D orientation of an object in space is hidden from you at the moment. With cubes, you can set the length and width and height of the cube to build a fair bit of things. So basically, if you adopt a Minecraft state of mind where everything is built up from cubes, you can make something relatively sophisticated. But again, if you're interested in that, you can jump ahead to to learning module P and play around with that. I'll just pause for a moment. Any questions about anything I've covered so far? Going once, going twice. Okay. Okay, so we've already talked a fair bit about joints. Obviously, they specify or they constrain how bodies move relative to one another. Here's how you would define a joint in ODE. Again, it was a little bit more complicated, but similar to what you need to do in PyBullet. There are different types of joints you can create. In this course, we're going to be mostly working mostly with hinge joints, things that constrain objects. Hopefully you can see my arm here, that constrain objects to rotate through a two-dimensional plane relative to one another. So like your knee joint or your knee joint or your elbow joint. You need to, when you're creating a joint, you obviously need to define which pair of links are being connected together. You need to define the position of that joint, where exactly that exists in space. Some of you may have already discovered that if you get the position of the joint wrong, you will actually see objects separate from one another. One aspect of joints that we haven't talked about yet are known as joint axes or joint normals, and I want to talk a little bit about this. This is another detail that's been hidden from you so far, but you are going to be able to play around with joint normals when we get to learning module N, building the quadruped. But again, for those of you that are interested in physics engines and want to jump ahead, you can have a look at this. Okay, so I am going to make sure that I can see myself for a moment. Okay, so imagine that I have my link, my upper arm, and another link, my lower arm, and I've attached them with a hinge joint here. And I want these two objects to rotate, these two links to rotate relative to one another through the plane that starts parallel to the screen. I could alternatively define, connect these two objects together so that they rotate, it's a little hard for me to do, they rotate relative to one another so that they're passing through this plane instead. So we can actually, when we're defining a joint, you can define a new data structure called the joint normal, which is a 3D vector. And the direction of that vector defines the 2D plane that the two objects are going to rotate through. So if I want these two objects to rotate through the plane that's parallel to the screen, I can define a joint normal that is pointing into the screen, and this vector, sorry, define a vector. This vector is normal to this plane here. If I want these two objects to rotate through this particular plane here, then I would define a joint that's pointing, I would define a vector that's pointing in this direction, this particular joint axis. And this vector here is normal to this plane here. Yeah, I hope that makes sense. Okay, so it's a little difficult to see in my cartoons here because it's difficult to draw in 3D, but bear with me here. So we've got X on the horizontal axis here, the Z axis pointing into and out of the screen, and the Y axis pointing up and down. We've got two objects, one here and one here. We're defining the fulcrum, or we're connecting these two objects together at 0, 0, 0. And I'm defining the joint axis, or the joint normal, as 0, x equals 0, y equals 1, z equals 1. So pointing upwards, the 2D plane that is normal to this 3D axis is the horizontal plane, the plane that sweeps through x and z, which means these two objects are going to rotate through the horizontal plane. If we take exactly the same two objects, same position, same orientation, we define again a joint that connects them together at 0, 0, 0. Oh, I'm sorry, and you can see, again, I didn't draw it very well here, but we can see these two objects are rotating through the XZ plane here. Anybody have any questions about that? Okay. Okay, let's move on and talk about contacts. This is in ODE, this was known as geoms. It doesn't matter really what they're called. We want to try and specify how objects interact when they come into contact with other bodies. There's lots of different ways this is done in physics engines. We want to keep some objects from colliding with others. If we tell the physics engine that there are certain pairs of objects that we do not want to interpenetrate, that they should stop when they come into contact with one another. The physics engine does this in a lot of different ways, but the main way it does this is to compute the distance between each pair of objects. And if the distance between a pair of objects is less than 0, those bodies should be pushed apart proportional to the amount of interpenetration. So imagine we have two objects suspended in space and they are moving at a high velocity towards one another. Remember, at every time step in the simulation, their positions are changing, and depending on their velocity, at the next time step, they may interpenetrate with one another. Physics engine computes the amount of interpenetration and then applies forces pushing them apart. If we have objects that are moving at a low velocity, then at some point they're going to interpenetrate by a small amount and be pushed apart. Alternatively, we may have two objects that are approaching each other at a high velocity, which means at some time step they may actually interpenetrate by a large amount, in which case the physics engine would push them apart with a larger force. Okay. There are two stages to dealing with objects that come into contact with one another. The first stage is contact detection, detecting that objects have started to interpenetrate, and then contact resolution. What should the physics engine do when it detects interpenetration? So let's start with contact detection. Let's actually start with the cartoon example down here in the bottom right. In this case, we have a total of 9 objects here, these 9 balls floating in space. As you can see in the simple cartoon example here, none of them are in contact with one another at the moment. In contact detection, we need to visit each pair of objects and ask whether or not they're in contact with one another. In this particular scene, we've got 9 spheres. How many potential contact events do we need to compute? If you have an idea, go ahead and type it into chat. So we need to determine whether this object is in contact with this object, and whether this object is in contact with this object, and whether this object is in contact with this object, and so on. Jared says 9, choose 2. That's right. That's one way to do it. If we have 9 objects, we can visit each of the 9 objects. And for each object, we can ask the question whether it's in contact with any of the other 8 objects. So another way to determine this is if we have n objects, we need to consider n times n minus 1 collisions, which in this case would be 9 times 8. Can we do better than that? Do we need to visit all 9 objects and for each object determine whether it's in contact with the other 8? Nick is correct. We can actually divide this by 2 because if we've already considered whether object I is in contact with object J, we don't need to consider whether object J is in contact with object A. Whatever the answer is, it's going to be the same answer. So in this case here, in the case of our n equals 9 objects, we have 9 times 8 divided by 2, which is 36 total collisions we need to detect. As you'll see in Nick's equation there, the biggest term in that equation is n squared. The thing that slows down physics engines, which you probably noticed when you were building your towers, is contact detection. That is the most computationally intensive step during every time step in a physics engine. There are smarter ways to do this, but basically the number of collisions we need to detect goes up superlinearly. And so as the number of objects increases, the number of collision detections we need to detect increases more or less quadratically. Turns out that different physics engines, again, come up with smart ways to do this. One way that this can be accomplished, like, for example, in ODE, is to define contact spaces. And I'm going to back up for a moment. I'm going to back up a moment to the preliminaries for ODE. We can see in this case we were defining just one contact space. So this is one space in which all the objects exist, and within that space we want the physics engine to determine whether any pair of objects are in contact with one another. You can be smart about things depending on your virtual environment by defining contact spaces and then placing subsets of objects into different spaces. What is a contact space? A contact space contains objects that are likely to be close to one another most of the time, but objects in different spaces are unlikely or rarely going to come into contact with one another. If we can perform this partition, if we can place objects into different spaces, this makes things easier on the physics engine. In what way? If you have an idea, go ahead and type it into chat. Contact spaces make it so that the physics engine most of the time doesn't need to compute all n times n minus 1 divided by 2 potential collisions. You might be able to guess from my cartoon up here of space 1 and space 2 how it might do so. So in this cartoon example here, I've told the physics engine that these 4 objects, they're going to come into contact with one another quite often. And these 5 objects are going to come into contact with one another quite often. But these pairs of objects are not, these 2 sets of objects are not going to come into contact with one another very often. A more concrete example of this is your towers that you built a little while back. You could have put all of the objects or all of the links in each tower into one contact space because objects within that tower are in contact with one another, but the towers weren't really into contact with one another very often until you knocked them over. Okay. So the intuition behind contact spaces is what the physics engine does is every time step is put a bounding box, put a space around these objects, and then it watches, instead of the positions of the object, it watches the positions of the bounding boxes. So now it's only, if we only have 2 spaces, there's only one potential collision that it's looking for, which is the collision between these 2 bounding boxes around these 2 subsets of objects. If those 2 bounding boxes do not come into contact with one another, then the physics engine's job is easier. All it knows that these objects and these objects are not in contact with one another. The only thing it needs to do is to look at the number of collisions within space 1, and it needs to detect any potential collisions in space 1 and any potential collisions in space 2. How many potential collisions are there in space 1 that contains 4 objects? You can use Nick's handy equation here. If you have an idea, go ahead and type it into chat. Exactly. So 4 times 3 is 12, but we only need to consider half of those, so we only need to determine 6 collisions. How about space 2? Exactly. So 5 times 4, 20 potential collisions. We only need to consider half of those, so 10. So in this cartoon example here, at this time step, the physics engine would only need to detect 16 potential collisions, 6 plus 10. But without using these contact spaces, it would have had to consider 36. So again, in this cartoon example, you can see how contact spaces has made our physics engine's job easier. And in many cases, if you choose your contact spaces wisely, you can greatly speed up your physical simulation. As I mentioned at the beginning of the time step, the physics engine was determining whether or not the bounding box 1 and bounding box 2 were in contact with one another. If bounding box 1 and 2 are in collision with one another, are in contact with one another, then any of the objects in both spaces might be in contact with one another, and the physics engine has to fall back on detecting potential collisions between all of the objects in both spaces. So we don't get this speed up all of the time, but collision spaces definitely help. Let's go back to robotics for a moment. Where do you think contact spaces might be helpful when simulating robots? What kind of robot applications or what kind of robot setups might you want to use contact spaces? If we're creating a virtual, when you have parallel runs, yeah, I think, Tyler, you mean when you have multiple robots running in parallel? Exactly. So if you're simulating not a single robot, but a swarm of robots, exactly, like the example with the walking robots. So if you have a single robot and it has multiple arms, and those arms or legs might come into contact with one another. We don't want pairs of legs or hands or fingers interpenetrating one another. So we could put all of the links that make up one robot in one space and all of the links that make up another robot in another space. Most of the time in that swarm, we're assuming the robots are not all on top of one another. They're physically separated. We can speed things up. If we don't use a contact space when we're simulating a swarm of robots, then the physics engine needs to determine potential collisions between any object in any robot and any object in any other robot. Okay, again, for most of you, this isn't going to come up, but it's a very important part of physics engines. If you're wondering, if you're creating, in your final project, if you create a very complex virtual scene with lots of objects and lots of robots, and your physics engine is grinding to a halt, this is why. Tyler asks, can contact spaces change dynamically, as in can the simulation automatically determine what objects should share a collision space as it runs? That is a great question. Absolutely, you can. There is a whole research community around physics engines, and because this is the rate limiting step, this is the thing that slows physics engines down, thousands and thousands of people have worked on this problem for a number of decades now. And there are more and more complex and automated ways you can define spaces. You can bring in machine learning, and you can have a machine learner, you can have a neural network learn statistics about objects. Those objects tend to be close to one another or not, and that can be used to predict or dynamically construct and destruct spaces. Yep. Again, for those of you that are interested in this, let me know, and I can point you to the literature on contact detection and resolution. Okay. Apologies. That's contact detection. Let's talk about contact resolution. So let's imagine that our physics engine has now detected that there are two objects that are close to one another. In most physics engines, there is a callback. You define a callback function. Some of you may have heard of callback functions before. This isn't a type of event-based programming, which means your code runs from one line to the next, usually, but every once in a while, if there is an event that occurs, your program jumps to a different point in your code. It jumps to a callback function. So you define a particular function that should be called whenever a certain event occurs. In ODE, this callback function would be called when two objects, object 1 and object 2, are in contact with one another. Again, this is code taken from another physics engine, so please don't worry about the details here. It's also written in C. I know that not all of you can write or understand C. It's okay for our purposes. Once this callback function has been called, it means that, for example, two objects are close to one another. Usually there are a number of checks that are performed first. Here's one check, which is to see whether those two objects are connected or not. Are they connected by a joint? As we've already mentioned, if two objects are connected, if they're connected by a joint, ignore this quote-unquote collision. Return from the callback function and continue doing whatever it is. If they are not connected by a joint, continue, meaning maybe we should do something about this collision. Assuming that this collision should be resolved, meaning that the physics engine should add some new forces to try and push these objects apart, most physics engines resolve contacts in the following way. ODE resolves it in this way, and so does PyBullet. It starts by sprinkling a bunch of points in the area or the volume of interpenetration. In my cartoon example here, we have two cubes that have come into contact with one another face on. So their two faces have come into contact with one another, which means we have a small two-dimensional small two-dimensional area where they've come into contact. The physics engine would automatically sprinkle a bunch of points in this two-dimensional space. If we have two we have two spheres that come into contact with one another, there is a small volume where they interpenetrate, and the physics engine would sprinkle a bunch of points in that volume. And you'll notice in the code here, again, the details don't matter. You'll notice the mention of contacts here, which is obviously this the fact that they're in contact. So we have these contact points, and we have a bunch of these points, not just one, because it's going to use each point to approximate the interactions between the volumes, the two pieces that have come into contact with one another. In ODE, each one of these points, you could define different parameters, which would define how forces are applied at those points to push the objects apart. You'll notice the mention of bounce here. So you can imagine, we can imagine two objects coming into contact with one another, and those objects may be bouncy or not bouncy. Imagine two rubber balls coming into contact with one another. Two rubber balls are going to be pushed apart with large force. They're going to suddenly have velocities. They're going to start moving in the opposite direction. Imagine instead we have two steel ball bearings that come into contact with one another. They are very not bouncy. They will hit one another and decelerate, but not necessarily accelerate in the other direction. So I've mentioned contact detection so far. We need to know whether a contact has occurred. We're now talking about contact resolution. What do we do when objects collide? Well, the obvious thing is we're going to apply forces to push them apart. But how we push them apart may depend. It may depend on the type of objects you're simulating. Okay. In ODE, these particular little contact points here were actually represented as joints. And this can be very confusing the first time that you've seen this. We've been talking about joints as things that connect objects together and allow them to rotate relative to one another. This seems counterintuitive. Why would we connect objects together with joints when the very thing we want those objects to do is be pushed apart? The reason why is to go back to the formal definition of joints, which is that they constrain the relative motion of the objects that they connect together. In the case of my hinge joint, in the case of my elbow, I'm trying to constrain the relative position of my upper arm and lower arm. I do not want the positions of those two objects to separate from one another. In the case of contacts, I want to constrain their motion in a very specific way, which is I don't want them to move closer to one another anymore. They can still move further apart. In fact, that's exactly what we want. But joints in general in a physics engine stop or constrain some subset of the way in which objects can move or rotate relative to one another. Just as a reminder, two objects in space have 6 different ways they can move relative to one another. They can change their horizontal distance from one another. They can change their vertical distance from one another. They can change their distance in and out of the screen from one another. So basically they're delta x, delta y, and delta z. That's 3 possible ways they can move relative to one another. And there are 3 relative orientations. So they can rotate this way relative to one another, this way relative to one another, and what did I miss? 1, 2, 3. Yaw, pitch, and roll. 6 different ways they can move relative to one another. Contact joints are a particular type of joint that constrains them from moving in the direction that they were previously moving in, right? The direction that caused them to interpenetrate. Okay. It's a lot of details. Again, all of these details are hidden from you in PyBullet, but it's, I think, useful to see. If you actually want to see, you can, in your own code base, you can navigate into the pyrosim directory and open pyrosim.py. And if you look for this particular function, get touch sensor value for link, you can actually see how these contact points are used. So imagine we have a particular link, and we're assuming that that link has a touch sensor attached to it. Again, for the undergraduates, that's exactly what you're doing this week. We're going to assume, we're going to start with a default value of -1. We're going to assume that that object is not in contact with the ground or other objects. We're going to sprinkle a bunch of contact points, or we're going to get a bunch of contact points back from P, which is PyBullet. So if that object with the touch sensor inside of it actually is in contact with the ground, for example, the physics engine will have already sprinkled some points within the volume or the area where the object and the ground have come into contact with one another. And if any of those contact points are associated with the link we're interested in, we set the touch sensor in that link to 1. So what you're seeing here is an illustration of, we're seeing an illustration of how PyBullet is actually resolving contacts. And we're seeing something else, which we're going to come back to in a few slides, which is we're going to exploit some of the things that the physics engine is already doing, like resolving contacts, to simulate aspects of our robot, which in this case is to simulate our touch sensor. So a physics engine on its own is not set up to simulate a robot. We need to build the robot-specific stuff, like sensors and motors, on top of our physics engine. And the way that we're going to build sensors and motors on top of our physics engine is to reach down into the physics engine and query or get back some of the information from the physics engine itself. Okay, I will pause again here and ask if there's any questions. Please feel free to type them into chat if you have them. Going once, going twice. Okay, let's move on. Okay, let's pull back for a moment, and we're going to try and put all of these pieces together. Abe is asking about the attendance sheet. If you go to the schedule, there's the attendance sheet for today. It's in the schedule itself. Okay, so let's pull back a little bit. Going back to your own code, you'll remember that one of the very first things you did in your code is create this for loop where every pass through the for loop is simulating one time step in your physics engine. What is the physics engine doing during that time step? It's doing a number of things, and the next time you go through your for loop, it does those things all over again. Again, those 3 or 4 or 5 or 6 things that the physics engine is doing every time step is hidden from you. In ODE, or Open Dynamics Engine, the physics engine we used to use in this class, you had to define all those things yourself. And here they are. So these are the things inside the sim loop here. These things were performed every time step of the simulator. The first thing the physics engine did is to determine who had collided with whom. For every collision, it would sprinkle these points, create contact joints that constrain the motion, and then it would apply a small force pushing these objects apart. Yeah. I'm sorry, I think I forgot to mention this before. At these contact points, the joints are actually applying forces themselves. The joints are pushing the objects apart in a similar way that your your elbow joint is pulling or pushing on your upper and lower arm to rotate them relative to one another. So joints can exert forces on links. And remember that the physics engine uses forces to determine the new positions and orientations of objects. Okay, so determine who is colliding with whom and add forces to those objects that are in collision. Add all the other forces that are acting on objects like gravity, friction, and so on. At that point, the physics engine knows all of the forces that are acting on every object in your virtual world, and it steps the simulation. This is the magic step. Inside, this is the magic part of your physics engine. Inside the step function, you will find somewhere in there A equals F divided by M, acceleration equals force divided by mass. The physics engine will use the forces on every object to compute the new acceleration for every object, and use the new acceleration for every object to determine the new position in space and the new orientation of that object in space as well. In ODE, it then does a little bit of house cleaning. It throws away all of these contact points that it had sprayed on interpenetrating objects. And then, depending on whether you turned on the graphics or not, it would draw all the objects in your scene. So basically, there are 3 steps in a physics engine. Compute all the forces, update positions and orientations, and then, if necessary, draw the results. Rinse and repeat. I'll pause again to see if there's any questions. Okay, we've got a couple slides left in this lecture. We're going to pivot now. We've talked sort of about the nuts and bolts of a physics engine. As I mentioned, when you're simulating a robot, there's additional details we need to add on top, which is mostly a robot's sensors and motors. So how do we do this? Let's imagine we want to simulate touch sensors. We've already seen how we do this in PyBullet. Let's imagine that we have this 2-legged robot here. We're looking at this robot from the side. Here's its body. Here's its front leg. Here's its back leg. We're going to assume that it has one touch sensor in its back leg and one touch sensor in its front leg, and there's some object out here in front of it. In this cartoon example here, at this particular time step in the physics engine, the back leg is in contact with the ground, but the front leg is not in contact with the ground. We can, if we want to simulate the touch sensor, we want to set the touch sensor in this back leg to 1. we could ask whether the near callback function has been called, and has it been called between this particular pair of objects, object 2, the back leg, and the floor, object 2 and the floor. If that near callback function has been called, the physics engine thinks those pair of objects are in contact with one another, and that's usually enough for us to set the touch sensor to true. Yeah. In this example here, this front leg, let's imagine the front leg here is called object 1. We can ask whether the near callback function between object 1 and floor has been called. If it hasn't, we set this touch sensor to -1. So in either ODE or PyBullet, we're exploiting contact detection and resolution to simulate a touch sensor. Yeah. What about if we want to simulate a light sensor? You remember from our Bratenberg vehicles, it had light sensors on the front of the robot. You might want to simulate a light sensor where we assume that this object out here in the environment is actually a light source. It's a light bulb, for example. Well, again, we can exploit the physics engine to compute a light sensor, to simulate a light sensor. Let's imagine the main body. Oh, I'm sorry, I misspoke before. Let's assume the body, the upper body here, the torso, is object 1. This is object 2. This is object 3. This is object 4. We're assuming object 4 is the light source. So at every point in time, we can again query the physics engine and ask at that point in time, what is the current position of object 1, which will give us back a set of 3 coordinates, x, y, z. Where does object 1 currently exist in space? We can do the same thing. We can ask for the position of the light source, so we can get the position of object 4, which gives us another set of coordinates. And we can then take the Euclidean distance between these two objects. So we now know how far apart object 1 and object 4 are. We're assuming that obviously the further apart these two objects are, the lower the light sensor is firing, the more in darkness that light sensor is. So we invert the distance. We take 1 over the Euclidean distance. So the greater the distance, the smaller the value of the light level. There's one last detail here, which is after we've inverted this distance, we take the square. Before we invert the distance, we take the square of the distance. Anybody know why? This might require you to think back to high school physics again. We're trying to compute the amount of light falling on object 1 here, the amount of light that's being cast by object 4 that actually reaches object 1. Nick remembers the inverse square law. So if you have a light source, and as you move away from that light source, the amount of light you're detecting falls off quadratically, falls off to the power of 2 by your distance from the object. So this is some additional code that you could build into your code base if you wanted to simulate a light sensor. You may or may not do that. Again, the details are not too important for us. What I want you to take away from this is we're again pulling out some data that our physics engine has already computed and using that to simulate something about our robot. Okay. For the undergraduates, next week you're going to move on to simulating motors. And again, in order to simulate a motor, we're going to exploit the physics engine. We're going to ask for information from the physics engine and use that to simulate a motor, which is going to apply force to a joint, and that joint is going to try and rotate the connected pairs of objects. How does this work? We're going to assume that we're going to send to our motor some desired angle. We want the relative rotation between pairs of connected objects to reach some relative rotation, some desired relative rotation. In my cartoon example here, let's go back to our two-legged robot here, back leg, forward leg, and torso. And we're going to imagine that there is a joint that is connecting the front leg to the torso. The joint is sitting right here. Whenever you connect objects together with joints, at time step 0, once you start the physics engine, the relative orientation between pairs of connected objects is 0 degrees. This can be a little bit confusing because if you look at this object and this object, it looks like their relative orientation is 90 degrees. Doesn't matter what it looks like. When you connect them together, their default orientation is 0 degrees. So if I create this object and I attach them with a joint, the relative rotation between these two objects is 0. If I create this object and connect them together with a joint, their